We are now going to look at the Wittig reaction, which allows you to convert an alkyl halide and an aldehyde or ketone into an alkene. This is a carbon-carbon bond formation reaction and is quite useful in the sense that you can add two different groups together to make a carbon-carbon double bond. This is done by first having an alkyl halide present. I'm just going to make this very general. Here's a nice little alkyl halide. And this reaction is a three-step process in terms of the order of reactions that you would go through. The first thing that you would add would be triphenylphosphine. And what you have here is a phosphorus, triply bound to 3 aromatic rings. There are 3 of those. And after you've done that, we tend to add a Grignard reagent or an alkyl lithium reagent. Basically, you need a very strong base present. So I'm just going to keep this one kind of simple. I'm not going to make it very complicated. But you do need to have a strong base present in your second step. And then finally, you would add the aldehyde or ketone that you were interested in adding to this particular compound. And we'll stick with the one we've been using for all of our other mechanisms. We'll keep it as acetone. This really is a three-step process. You do have to do 3 separate reactions. So let's go through each of these one step at a time. Triphenylphosphine. I'm going to talk about it and then I'm going to give you an abbreviation for it. It's a phosphorus with 3 aromatic rings coming off of it. And we often will denote this as phosphorus, and we have pHs to represent phenyl rings. This is commonly used, or we just say pH3 to make this much more simple. But these are the different chemical species. These symbols, all represent the same chemical species. They're all exactly the same. And what we use this triphenylphosphine for is as a nucleophile. That's what its purpose is going to be in this first step of the reaction. Since the phosphorus has a lone pair of electrons. And we put this in solution with an alkyl halide. Now I'm assuming that at this point you guys could build any alkyl halide that you wanted. Now, based on whether it be primary, secondary, or tertiary, you should be able to go through an Sn1 or an Sn2 substitution. In this particular case, we would be doing an Sn2 substitution. But you will have the phosphorus come in from behind and kick out your leaving group, which will make an alkyl triphenylphosphonium halide complex. So you still have the backbone that you had previously, but instead of having the halogen here, we have the phosphorus. Now the phosphorus has a positive charge at this moment in time, and just so that we know what else is present on this carbon, there is also a hydrogen here. I just want to make that clear so that we can see what groups are present. And there is also a bromide as our leaving group. That's what you get after the first step of this reaction. This is alkyl triphenylphosphonium halide. And this is a fairly stable complex. It has nowhere to go. This is when we add the Grignard reagent or the alkyl lithium reagent. You need a very strong base here to remove this particular proton. It's very important that when we do these types of reactions that we do it with a primary alkyl halide or a secondary alkyl halide so that we can have a proton attached to the carbon where the substitution had occurred. If you do not have a proton there, you're going to have some severe problems. So you cannot do this with a tertiary alkyl halide. But a primary or a secondary, those would be appropriate for what we need to have happen. So at this point, you would add the alkylithium reagent, and the one that I had used, oops, wrong color, a moment ago, was this guy. And again, I like to draw them as ionic complexes since I can see them better. This carbanion is an extremely strong base, and it very much wants a proton. The most acidic proton is the one attached to the carbon that is attached to the phosphorus. And there are reasons for this. This is the most acidic proton because by removing it, we will have the ability to produce a phosphorus ylide. So as we remove this proton, the carbon-hydrogen bond will break and carbon will get those electrons. Now, it doesn't really want to lose those electrons or do anything else with it. There's no leaving groups present nearby. It needs to maintain an octet, so it does keep that pair of electrons with it. After this part of the reaction has occurred, we make this phosphorus ylide. And those guys are just our spectators. The important part is this phosphorus ylide, or you can call it a phosphorane. It is overall charge neutral, but there are formal charges in the molecule, and they are adjacent to each other. That's what makes something a ylide. They have formal charges, they balance each other, so overall you are charge neutral, and they tend to be right next door to each other. That's what makes something a ylide. And this one in this case is phosphorus, so we call it a phosphorus ylide. Now once the ylide has been made, it can be added to an appropriate ketone or aldehyde. And it will go through the next set of reactions. And it tends to give two different alkenes. You can make the Z-alkene or the E-alkene. And it has to do with the type of ylide that you have formed here, which one is more likely. Unstabilized ylides, those that lack a carbanion stabilizing group like this one, you don't have something that could help stabilize that negative charge, they tend to predominantly give the Z-alkenes or the cis-alkenes. If you have a stabilized ylide, those that have a carbanion stabilizing group through resonance with an electron withdrawing group, which this one does not have, they tend to predominantly give the E-alkenes or those that are trans. So you can tell which one should be major or minor during the course of the reaction based on the type of ylide that you have to begin with. I'm not going to be too concerned with that in my class. I'm just going to be concerned that you can make the different products when that is appropriate. So, in the third step of the reaction, you would add the aldehyde or ketone. And for our purposes, I said we would use acetone. Not all ketones are symmetrical. I've deliberately chosen one that is so that you don't have E and Z products. But if it were asymmetrical, be aware you would have the E-alkene and the Z-alkene that would form as a result of this. Now, as you look at what we have here, notice that the ylide literally does have a positive charge and a negative charge. It is very easy to figure out what binds where if you think about charges. If you look at the aldehyde or ketone, you're looking at the carbonyl group. I hope you remember that the oxygen is more electronegative than the carbon. So the oxygen is partial negative, and the carbonyl carbon is partial positive. And I hope you also remember the opposites attract. And so the negative part of the ylide should be attracted to the positive part of the aldehyde or ketone. And the positive part of the ylide should be attracted to the negative part of the aldehyde or ketone, since opposites attract. So this anionic part, this carbanionic part, it will act as a nucleophile and add to the carbonyl carbon. Now, as that is occurring, carbon can't have five bonds. So you're going to break the pi bond and give those electrons to the oxygen since it's more electronegative. Oxygen will now get more negative character, and it will use that negative character to form a bond to phosphorus. because that's positive. So we're going to make what's called an oxaphosphatane intermediate. I'm going to try and draw this out in such a way that you can see it really well. Okay, so there's this 4-point intermediate that is going to form. The phosphorus also has those 3 phenyl rings attached to it. And what was the anionic carbon had a methyl group and an ethyl group attached to it. If you can't remember that this is so, go back a minute and note that it does have the ethyl group and the methyl group here. The carbonyl carbon, in our particular case, had the 2 methyl groups attached to it. So you need to remember what's attached to what atom. So go back for a minute and note that on the carbonyl carbon you have a methyl group and a methyl group. So be aware of which carbon is which. This was the green one in our last example, and this was the blue one. So the one in green was the carbon from the Ylide. The one in blue there is the one from the aldehyde or ketone. And if you can remember which one's which, you should be able to get the right groups attached as you form this oxaphosphatane intermediate. Now hopefully you remember 4-membered rings are not all that stable, and they are going to rearrange. So we like to relieve that angle strain. The most polarized bond in this molecule at this moment in time is the carbon-oxygen bond. That one has the greatest difference in electron negativity. And so it will break. And as it breaks, oxygen is the more electronegative atom, so oxygen takes that pair of electrons. As that is occurring, the carbon there in blue is losing electron density, so it's going to need some more because it wants to maintain an octet. And so the carbon-phosphorus bond, the bond to the green carbon, the carbon-phosphorus bond is going to break. And carbon is more electronegative than phosphorus, so carbon will take those electrons and use them to make a carbon-carbon double bond. Now as this happens, we will be able to make our alkenes. Okay, this was the carbonyl carbon, and this was the carbon from the phosphorus Ylide, which was initially the carbon of the alkyl halide. Those are the 2 carbons that have come together to form this carbon-carbon double bond. In addition, we've also had the ability to form triphenylphosphine oxide. Okay. So this is how we do it. Now, again, if I had the ability to make cis and trans alkenes, I would have them, and I wouldn't be too concerned about you trying to figure out which one's major and minor, but I would be concerned that you can make both alkenes.